And then for the last talk for this session, we have Mark Pinsonneault from the Ohio State University talking about astroseismology with the galactic bulge time domain survey.
Yes, thank you very much. Appreciate the opportunity to come and talk about this exciting opportunity. And one of the major drivers for this is that time domain astrophysics has absolutely revolutionized stellar astrophysics. There's a lot of exciting discovery space in the center of the galaxy. And so I wanted to talk about our progress on doing this and how well we think we can accomplish it. I also note that this is part of a team indicated here. We have people interested in seismology, people interested in galactic populations, liaisons to surveys, and various other folks. So this is not in any sense things that are just me that I'm describing. I'm representing a group. So I always like to begin with a motivation. And to me, one of the key motivations here is I think that the galactic bulge is a fascinating but really not very well understood population. I believe it's entirely possible, for example, that we will find out that there are populations that are unexpected there. There are very metal-rich stars, very metal-poor stars. The mixture of heavy elements could be radically different than in the solar neighborhood. There have been claims that the helium abundances are enhanced. This could affect planet formation. This could really affect the interpretation of the microlensing planet survey and inform our studies of the galaxy. And if you wanted to do this, I'd argue that cool evolved giants are perfect stars to do it with. They are bright enough that it's feasible for us to use high resolution or medium resolution spectroscopy to infer their chemical mixtures and temperatures and other properties. These giants are pretty numerous. They're a well understood population as a group. And the other point is that because we have this wonderful time domain survey for microlensing, it is ideally suited in cadence and depth to measure ages of these stars, something that you can't get with photometry or spectroscopy easily through the tools of astroseismology. Now, I think I'd like to talk a little bit about how astroseismology works because the physics is really beautiful and really clean. The envelopes of cool stars have spots on their, have basically turbulence in their outer layers. This turbulence generates sound waves and water waves. Stars are held up by pressure gradients and density gradients, which means waves are refracted as they go in. They will bend and come back if the frequencies or the wavelength are large enough compared to the density scale height. They will be reflected back down from the surface. And as a result, you will get standing wave patterns that produce brightness fluctuations that can be identified. What you're seeing here, okay, and I'll see if I can make this work. One never knows. Let's see, let's try this. There we go, the big purple circle. What you're seeing here is these are solar-like stars with periods characteristically of about 5 minutes, amplitudes at very low part per million, few part per million levels. As you move up to stars with lower and lower surface gravities, they basically switch to lower frequencies because that's what's trapped at the surface. The amplitudes rise dramatically, and you also have a whole bunch of distinct modes that you see. The spacings between these modes tell you about the mean density of the star, so you can measure the masses. And if I have a mass and a radius and a composition through some means, I can figure out the ages of giants using the population stellar evolution theory. Now, the other point here is what kinds of stars can you actually reach? This is data from the Kepler field, an upcoming APOCAST 3 paper. These are all stars at almost exactly solar metallicity. The colors are different ages. And the point is the luminous upper red giant branch is going to be high amplitude stars, easier to detect with seismology, but these stars are relatively rare in stellar populations. If you can get down to the red clump population down here, these stars are in a very similar place on the HR diagram, but have very different astroseismic properties. It's a beautiful age tool. And if we can get down to here, I contend we'll be able to learn really, really interesting things about the ages and populations in the center of the galaxy. Now, so at this point, you might ask, well, why do we need Roman? After all, we have these carbon-based life forms like me, but there are robots in the world, and we can do machine learning. And so we can just take the astroseismic data we already have, let the robots solve the problem, and who needs us, really, anyway. But the problem with this is that if you do this, it turns out that the stars that we observe, the stars that Kepler and the like have observed, are actually all pretty local. They don't actually sample the populations in the center of the galaxy, and the robots can't learn about things they don't know. And so as a result, it turns out that these machine learning tools have great difficulty in recovering populations that aren't in their training sets. You might say, well, the TESS satellite is going to solve our problem. The TESS satellite is another time domain mission, huge astroseismic sample, but TESS is tiny. The stars that it studies are bright, and so it's a huge, incredibly local sample of stars that we're getting with TESS. And so if you really want to understand the center of the galaxy, you really want to use a mission like Roman to do it. Now, the initial simulations here from a really brilliant early paper by Andy Gould, Dan Huber, and others basically demonstrated that if you took Kepler-like curves, used what the performance of then W first, now Roman is, you would say that if you were looking at lower red giant branch stars, the amplitudes are low, it would be very hard to see a signal. The red clump ought to be detectable. The bright giants ought to be relatively easily detectable. And if you took these simulations and said, what do you see in the center of the galaxy? Roman is a gigantic opportunity, right? There's 500,000 or more targets that we expect to be able to see in the center of the galaxy. Now, the question is, well, is this actually, true? And to make sure we figure out whether it's true or not, we would actually like to be able to actually do more detailed simulations or studies. So the first thing we did is we're doing detection simulations. That's one aspect of the work, and Noah Downing has a nice poster out there describing this simulation work. And there are two really, really important ingredients we have to worry about. The first of these is, and I find this utterly bizarre, the stars that we're interested in are saturated in the first read at the galactic center. Basically, we really wish that this satellite was a little bit smaller. A smaller mirror would actually solve our problems. And so as a result, that means we have to worry about the ability to do saturated star photometry. And so Matt Penny, in one of his noise models, argued that you have a kind of a floor at about a millimagnitude, these red lines here. That's one of the models we work with. And you already heard from Robbie about his very interesting simulation work where he claimed that you might be able to do better than this for bright stars. And so these are two noise models. The other thing that we're interested in looking at is whether or not we look at it once every 15 minutes or once every 7.5 minutes. And so we consider both of those cases as well. Now, this noise floor challenge turns out to be key because the initial simulation work I showed you by Andy Gould was very optimistic about its ability to do accurate saturated star photometry. So if we actually have a millimagnitude limit, our initially lovely kind of simulation detection here becomes kind of ratty. And so as a result, it becomes much harder. A figure of merit to keep in mind is the amplitude of oscillations in the red clump is of order a millimag. And so if the noise is at a millimag, we're right at very close to the noise floor. It's a hard measurement. If you do sampling twice per 15 minutes, by contrast, it actually makes a really significant difference or apparent difference in detectability. We then ran some hundreds of stars of simulation with simulated Kepler data. In this case, this represents some very recent results, but ones that we believe are pretty robust. In this case, you can think of the y-axis, Numax, as a kind of a luminosity or gravity proxy, bright stars at the top, faint at the bottom. This is temperature, cool to bright. Top panels are the red clump stars, bottom panels are the red giants, and the green is good, yellow is maybe, red is nah. And in this case, the point is with the notional sampling, we are able, we think, to detect at least some of the stars in the red clump, but this is going to be a marginal detection. In other words, we're going to have to really work at this. If we will detect in all cases the luminous red giants, but there's not as many of them. And that means that relative to those yields I've talked about, this strategy could drop our yields by up to about a factor of 3, relative to the more optimistic noise models. Now, if we adopt Robbie Wilson's model, we see that we recover almost everything. That indicates that we're actually really close to threshold. And so this is an equivalent to saying that another path to getting a very large number of seismic detections is actually to be able to do really good saturated star photometry, really precise saturated star photometry. If we have a higher cadence in the middle, you can see that in the higher cadence, we robustly recover the red clump and do extremely well on the red giant branch. And so the first piece of this work, the simulation work, is ongoing, but our kind of bottom lines are we're very confident we're going to have some astroseismic detections. The number depends on the noise threshold. The number depends on the sampling rate. And we would argue that it would actually be really good if we could have a higher sampling rate in at least some fields. Now, the next piece is the population simulations. And for this is the work that you heard about from Trevor Weiss in his lightning talk yesterday, a very nice poster. The initial work that we've done in the simulations actually involves just basically taking the Gould noise model and the yields, which are fairly optimistic, and using the existing footprint and some other proposed ones. We also looked at adding a footprint in the center of the galaxy, which is great because it solves our saturated star problem. Turns out that all of our red clump stars are now hiding behind a nice screen of dust. And so everything gets easier for us in that regard, although the source counts take quite a hit from the other side consequences of this. And so the bottom line is that we're going to be looking at this. We're going to be testing different extinction models, different galactic population models here. But we actually think that this is potentially an extremely powerful tool. Now, the last piece I'm going to talk about here is, so far I've talked about, well, you can measure seismology. Well, seismology gives you information about mass, but if you care about age, you need to know about composition. And that means that there's another really important ingredient, which is how well can you characterize the stars. And in the second piece of the work we're doing here, we're going to be focusing on this characterization. There's really two tools that we will be trying to use. The first of these is we're going to try and leverage high-resolution spectroscopy. There's some existing high-resolution spectroscopy from Apogee, but we think we can get more from Apogee and other surveys, which we will then use to train moderate resolution or low resolution things like Gaia BPRP, and then try to use those in turn to inform photometric estimates of things like metallicities. The other piece is that was alluded to earlier in the conference is we're actually very interested in using the diffraction spikes in these images to centroid the images extremely precisely. We can then get parallaxes, which could then be used to infer radii of these stars, which greatly improves the precision of the ages that we can obtain. And in addition, I think quite interesting to other science cases in the galactic bulge, where you could actually get really, really nice parallax maps of this. And so to summarize, we think that astroseismology is an exciting prospect for Roman. In fact, I would argue that looking at the landscape of the upcoming time domain missions, Roman is probably the most interesting to me astroseismology mission that we have upcoming in the sky, the most interesting new one that we will get. Having a higher cadence is actually going to be really, really powerful for unlocking the true potential of this tool. If we can reach that red clump population, we actually will have a really rich set of diagnostics, and I would contend that we are almost certain to find surprises about the populations in the center of the galaxy by doing it. And we have upcoming work where we really hope to take advantage of some of the beautiful simulations we saw about saturated star photometry, trying to explore astrometry and other things. I will stop there and thank you very much for your patience at the end of the day.
Thank you, Mark. Any questions?
Thanks for that. That certainly got me thinking. Remind me what precision you need on the relative photometry of your saturated stars from
the amplitudes we're looking for in the clump are of order a millimagnitude. Okay, so in other words, we need kind of measurements at that characteristic level in order to be able to see those signals. The more luminous giants have higher amplitudes, but there's fewer of them.
Okay, thanks.
No, that's good.
Mm-hmm.
Mark, that was a really exciting talk, and it's nice to see that the traditional discipline of astroseismology still has a lot to give us with these new instruments. I wondered, as kind of an outsider to this field, about the role of stellar rotation, because my understanding is that can also influence the propagation of the waves, as one could imagine through, Coriolis forces. And how well do we understand how these, stellar rotation couples to all of this, such that, we could measure the properties from this?
Yeah. That's another really interesting domain. The first thing is from the point of view of oscillations, rapid rotation is largely bad news. It actually disrupts the standing wave pattern. And so that means in rapidly rotating evolved giants, we tend not to see seismic signals, but that's only a couple % of most of the stars based upon detailed work in Kepler. Measuring stellar rotation periods is another fantastic tool. I respect people who do that. That's actually more technically challenging than measuring astroseismology, I would argue. But it's an exciting avenue if we can do it, because rotation period is tied to age, and that could tell you really interesting things about ages of main sequence stars as well.
Thanks, Mark. This is the bulge survey, but
Yeah.
you know, we have 25% of our time for doing other surveys. Where else in the sky would be particularly compelling to do general astrophysics surveys that have astroseismology components?
Well, if you were interested in that's a great question. If you're interested in the really luminous giants, when the periods become weeks to months, even, or even years in the case of the most luminous ones, it turns out that you might be able to imagine a survey strategy even that could be compatible with a high latitude time domain survey, where you actually could try to sample things over periods of hundreds of days sparsely, and then you might be able to get some signals. In this case, the amplitudes are huge. There are several percent, and so the precision of the measurements is no longer a major factor. It's the time domain filling factor. Other thing would be fantastic, globular cluster. Just find one, just park on it. That would just be great. I don't even know what I'd love to see you do that. Yes.
So, do you need a continuous high cadence measurement, or if you have a same number of the data points, if it can be the sparse sampling, but you can hold it, kind of things?
The characteristic periods we're talking about are very short compared to a typical Roman campaign of 72 days. That means, in other words, we don't really care whether the 72 days are at the beginning or the end of the 5-year mission. We do care that each individual one, basically we need a series of data which is long compared to the oscillation period. And since the oscillation period is, 12 hours, as long as you're kind of evenly sampling it over a period of a month or something like that, we're fine with that.
Okay, if there are any other questions for Mark? If not, thank you.
Thank you.